Nuclear stability is nothing more than a measure as to the energy required to overcome that positive repulsion of protons, all right? And it's a pretty big amount, all right? Electromagnetic force is nothing to mess around with, and keeping those positive forces apart from each other is pretty intense. It's mostly the strong nuclear force, tiny bit of weak maybe, but we're not going to talk about weak too much. Mostly the strong force for our case. Strong and weak forces are stronger than electromagnetic force or gravity, and it's mostly the electromagnetic force we have to worry about, keeping those positives apart from each other. Nuclear binding energy, which gets the symbol E sub B, is a method that scientists can use to estimate the force contribution, like how much energy does the strong force have to contribute to keep the nucleus safe. And that's a kind of calculation we're going to do here in a little bit, which is really pretty cool. There's some interesting applications of the nuclear binding energy values we're going to see. And so get ready, hang on. But anyway, what we're going to look at here is how to calculate the nuclear binding energy. The nuclear binding energy, E sub B, is the negative of the energy change if the nucleus is formed directly from individual protons and neutrons. So what we're going to do here is we're going to do an example of this EB calculation. And let's say it was for a helium nucleus, a helium-4. Well, helium-4 comes from 2 protons and 2 neutrons. So we're basically going to do a delta E, an energy change for that reaction. All right, 2 protons plus 2 neutrons making a helium-4. And whatever number we get, we're going to take the negative, the opposite of it. So binding energies will turn out to be positive numbers. And if all of that was as clear as mud, well, let's get into an example and I'll show you what I mean here. Let's calculate the binding energy for making deuterium. Deuterium is an isotope of hydrogen. It's hydrogen 2. Deuterium is sometimes referred to as heavy hydrogen. But anyway, in this process, you would take then 1 proton and 1 neutron, add them together to make hydrogen 2. And you can see this is a balanced reaction, etc., etc. The protons plus the neutrons making the atom is what you want to do for these binding energy calculations. Well, you can actually figure out the masses of the proton, neutron, and deuterium. Deuterium has been studied a lot, and the mass of the deuterium is 2.01410. Since Chem 221, we have had mass values for protons and neutrons. The neutron is a little bit heavier than the protons, 1.008 versus 1.007, etc. But an interesting thing happens here. If you add up the proton and neutron mass and you compare it to the deuterium, whoops, we've got a problem, because 2.016475 is certainly bigger than 2.01410, i.e. the mass we put in is not equal to the mass we get out. And as a chemist, that's like brr, brr, red alert time, sound effects not necessary, all right? But wow, mass not equaling the mass that comes out, this is like breaking all the law of mass action kind of things that we talked about in balancing chemical equations and stuff like that. And that's kind of trippy. So the mass is not conserved. You're actually losing mass on going from a proton and a neutron to the deuterium. You have a negative delta M. Remember, delta is always final minus initial. So final 2.01410 minus initial 2.0164775, you get this negative number. And again, you might be thinking, Russell, you made me go through all those balancing chemical reaction things back in Chem 221, and maybe it wasn't that important. Oh, it is important. There's something else going on here, because if you think about it, for some reason, a proton and a neutron must make deuterium. And what is that reason? Well, thank the stars, Einstein came around. Woohoo! And Einstein, one of his famous equations is E equals mc squared. And in this problem, we're going to talk about the change in energy, delta E, equaling the change in mass, delta M, times c squared. Now, we need our energy to be in joules, and a joule is a kilogram meters squared per second squared when you break the units down. This is something in the SI units we talked about quickly in Chem 221. So what that means is our delta M in grams per mole, we have to turn into kilograms per mole. So notice that 0.00239, when you divide by 1,000, becomes negative 2.39 times 10 to the minus 6, all right? So you need to turn grams per mole into kilograms per mole, but if you do that, you can then multiply by the speed of light squared. Speed of light we talked about in Chem 221 as well. It's 2.998 times 10 to the 8th meters per second. So if you square the speed of light and you multiply it by the kilograms per mole, you're going to get an energy which is in joules per mole. Now let's just stop there for a second. Delta E negative 2.15 times 10 to the 11th joules per mole. And that would be negative 2.15 times 10 to the 8th kilojoules per mole. That number is massive compared to the types of delta E's we've looked at since the thermodynamic chapter in Chem 221. I mean, acids plus bases, we'd maybe get like 10 to the 3rd kilojoules per mole, or combustion reactions we looked at sometimes in Hess's law, or even recently when we did energy transitions of taking like ice and turning it into gas, water, or something like that. Even those were, 10 to the 3rd, 4th kilojoules, nothing too big. This is a big, big amount of energy. And this negative energy is basically the reason why elements form from raw protons and neutrons at all. It is the price, the money you get out for making these isotopes. And it's huge. All right. Generally speaking, exothermic reactions are the ones that happen. And because this is exothermic, i.e. negative, and it's freaking large, just a huge number, this is why atoms form. Binding energy equals the negative of the delta E. So in this value, when I turned the E sub B, first of all, I went joules per kilojoules, which means I divided by 1,000. And I also turned my negative into a positive number. Binding energy is the energy required to keep the nucleus stable. I want to backtrack just a little bit. The delta E was massively negative, massively exothermic. And that really is a justification for why atoms form. If there wasn't a reason for atoms to form, we would have just random assortments of protons, neutrons, and electrons floating around the universe, i.e. carbon and DNA and caffeine. Woohoo! These kind of things would never form, all right? So a huge delta E like that, a huge negative delta E, is just justification for why the atoms form. And oh yeah, they want to form, all right? As the delta E becomes more negative, you have more likelihood of the atoms forming. We'll talk about that here in a little bit. But binding energy is always the opposite of the delta E. So you take the positive version. I turned the joules per moles into kilojoules just because that's what people usually do. Pretty cool. The binding energy here, the very positive, just means that you have lots of energy saved through the stabilization, through making the atom. All right, and that's kind of cool to know too. Binding energies, a lot of times they'll talk about binding energy per nucleon, and a nucleon is just a particle in the nucleus. So in this example, we had 1 proton plus 1 neutron, or 2 nucleons. So if you take that 2.15 times 10 to the 8th, and you divide by 2, that's going to give you the kilojoules per mole of nucleons. And that's the amount that people feel is what the strong force contributes to keep the atom stable. So without that kind of energy, you wouldn't be able to form the atom at all, the heavy hydrogen, because the protons would try and stay away from each other. Now, again, this is hydrogen, so you'd only have 1 proton. You might be able to squish that number a little bit, but still, it's pretty massive. Strong force, definitely pretty important. Scientists have collected binding energies for nuclei for a whole bunch of different processes. And you can see down here in the lower left, here is deuterium, heavy hydrogen, and the value 1.08 times 10 to the eighth, whatever it was on the last slide, you can see it's about right there. So that's pretty cool, and that's a heavy hydrogen. However, they've done this for all the different isotopes on the periodic table, and you can see there's all kinds of different numbers on there. If you look at that table long enough, and again, there it is again, you'll see that iron 56, which is right there, that's the top of the curve, all right? And people consider iron 56 to be the most stable element thermodynamically. And we see this kind of stuff. If you know about astronomy, a lot of times when the suns go nova or supernova, a lot of times iron 56 is like the end, like it can't make any more energy. And that's when the sun begins to break down. So even the power of the sun is unable to make more than iron 56. So if you look at that binding energy curve, there's a bunch of atoms less than iron, which are getting more like iron, but there's also a lot of elements and atoms that have heavier masses that also want to be like iron. So iron literally is the end of the cycle. Once things create iron, the atoms kind of stop. There's no more processes that are going to happen. So atoms that have less than 26 protons, that are less than irons, they're going to use a process called fusion to become more like iron 56. On the other hand, the atoms with more than 26 protons, i.e. greater than iron, will undergo fission to become more like iron 56. And we'll talk about that here in a little bit. But I want you to think about this a little bit. All of the carbon in our bodies and the oxygen we breathe and the hydrogens and the magnesiums and the nickels and everything else, they all want to be like iron 56. And so do the heavier ones, uraniums and leads and tins and things like this. They all want to be like iron 56. So one day, if the universe becomes essentially all iron 56, that's it. That is thermodynamically the end of everything, because once you get to the more stable place, there's no more energy out. There's no more making future elements. And on one level, that's kind of freaky because, yeah, once you get to iron 56, the universe stops, game over. All right. Fortunately, though, good old kinetics, the study of speeds of reactions, comes to help us out here a lot. Making iron 56 from carbon or deuterium or whatever is incredibly slow. It has a massive energy of activation that has to be overcome in order for the iron 56 to happen. These elements don't just naturally turn into iron 56. It's a pretty high energy process we're going to see. And so because the energies of activations of these reactions are so slow, none of us have to worry about the universe becoming iron 56 and game over like I just prophesized earlier. No way. The energies of activation are just massive, way off the scale for human things. So no one has to worry about iron 56 becoming the only element in the universe, although that might make a cool science fiction story, but I digress, and I think my prophet fell off. Just realize kinetics is kind of the helper here. So just like kinetics is going to prevent anyone from having to sell their diamonds, because diamonds will all go to graphite one day, the energies of activation are huge, so no one has to worry about all your diamonds decomposing to graphite. No one has to worry about hydrogen, carbon, oxygen, nitrogen, etc., turning into iron 56 anytime in the near future, all right? The energies of activation are just so massive that the reactions are super slow. Almost no atoms have enough energy to overcome it. It is kind of a cool thing to think about, though, if you're a thermodynamic scientist. This is the kind of question you might see. It says, which of the following nuclei has the highest binding energy per nucleon? And there are 4 atoms listed, and a 5th says none of the above. Well, if you happen to be able to look up, or you have a table of binding energies per nucleon, you can look these 4 up and see which one has the highest binding energy per nucleon, stuff like that, which is totally cool. However, if you don't have a table of binding energies per nucleon next to you, what? You don't have one next to you all the time? Just joking joking. I don't have one either. Anyway, what you can do is you can look and think about which of those atoms is closest to iron 56, because iron 56 is the thermodynamic endpoint for this kind of discussion. So helium and lithium, A and C, are definitely much lower than iron on atomic numbers. Thorium is much higher than iron, but nickel, all right, answer B, nickel is pretty close to iron. So if you look up the values for the binding energies here, the nickel is definitely going to be the closest one. It has the highest binding energy per nucleon because it's closest to iron. So that's a nice way to kind of guesstimate on these things, and if you look it up, you'll see that's the answer too. When the atoms are smaller, they wish to become more like iron 56, i.e. get bigger. And the process that's used to do that is called fusion. It's a nuclear fusion of atoms coming together. Fuse means to combine. So smaller nuclei are combined to make larger nuclei. And nuclear fusion is fascinating on thermodynamic levels, but it's also really helpful to us as people because you can actually, in theory, use fusion to create energy. In the reaction that's shown below, you have heavy hydrogen, hydrogen 2, and tritium, hydrogen 3, and it makes an alpha particle plus a neutron. But notice the energy release there. It's negative 1.7 times 10 to the 9th kilojoules per mole, and that's a lot of energy released. So if human beings could formalize the use of fusion power, we'd get a lot of energy out, energy used for electricity and cars and all that kind of stuff. The problem with nuclear fusion, though, is that it has a very high energy of activation barrier. And if you're going to make this happen, you need to use plasma. And we'll talk about plasma here in a little bit. The good thing, though, about fusion, it's a very clean energy. You put in hydrogen, you get out helium, all right? So something happens in your fusion reactor and you have to stop it. Well, no problem. You've got hydrogen, which is flammable, so no smoking in the lab, and you have helium, which you can contain pretty easy too, but there's no messy like leftovers or anything like that, which is cool. Meltdown is a problem with fission we're going to talk about. So if fusion stops, it just literally stops. There's no wastes. It's pretty cool. But we do need to use plasma. Plasma is actually another state of matter. So in Chem 222, we've talked so much about solids, liquids, and gases. Plasma is a fourth state of matter. It's just as important to scientists as the other ones are. Plasma is an electrically conducting fluid. So it literally like flows, but it has positives and negatives. And the electrons kind of roam over the liquid, quote unquote. This is a really hard substance usually to control. So usually you need strong magnetic and electric fields, and it's going to be very hot. Now, the interesting thing is that if you think about the universe, all right, most of the universe is not made up of solids, liquids, and gases. Most of the universe has plasma because plasma is in the sun, and of course the suns are huge. You've got the solar wind, you have lightning on the earth and things like that. So most of the universe is actually made up of plasma, and it's only on these weird places like the earth where you have an overabundance, if you will, of solids, liquids, and gases. So it's kind of cool to think about. On the Earth, of course, plasma is not as common, so that's why plasma isn't discussed as much. But in the universe, plasma dominates. This picture right here shows different plasma sources, all right, and it's listed by temperature and density and stuff like that. In the upper right-hand corner, you've got like suns, fusions, and stuff like that. Those are where most of the plasma is. But on the Earth, you can see there's lightning kind of in the middle part. If you saw the eclipse in Oregon a few years ago, the corona was basically a plasma ejection. Fluorescent lights have plasma in them, solar winds, nebulas, and stuff like that. So there's a lot of sources of plasma. They're just not as common on the Earth, or we don't think about them as much.
There's a match head. Nice.
This video was created by two of my students in 2010, and they're wonderful people, and I respect them so much, and they're in medical school. They're doing great things. But anyway, at the time, I said, oh, well, plasma is really difficult to create and stuff like that. You need high energy and stuff like that. And they said, hey, what about the grape experiment in their microwave? And I'm like, what? So anyway, these guys put a grape in their microwave with a match head, you can see. And when they turned the microwave on, this really bright light occurred. And I thought, no way, this isn't plasma, which is what they claimed it is. Well, I did some research, and I'm not convinced that it's not plasma. Okay, I'm not going to say I totally believe it's plasma. I still think it's some kind of reaction, maybe with the match head, but I can't totally kick out based on the research I did that it isn't plasma. So maybe you just saw plasma created in a microwave, and you can try this experiment too. I take no responsibility for any damage to your microwave because, again, plasma is a super high energy source, and I keep nervous. But they did it several times and made this video for me. So my hat's off to them. This has given me a lot of things to think about. It very well might be plasma. I can't totally say it's plasma, but I certainly can't say it's not plasma, which is where I started this whole research part. So again, my hat's off to them. And if you see a way to make plasma, you let me know as well. People are trying to make usable working of fusion power, because if they could, the energy created would be fantastic. And there are various groups around the world that are trying to create a fusion reactor that would create sustainable fusion, which we could use for energy, which would heat our water, make electricity, et cetera, et cetera. One of the more promising possibilities is what they call a tokamak reactor. And a tokamak is kind of cool. It's basically like a donut. All right. And in the donut, you have high energy fields, magnetic and heating. And so the plasma is created. And from the plasma, then they can actually induce the fusion to happen and create energy outside of it. I think this is a pretty promising area of research, but again, it's still under development.
Plasma, the fourth state of matter. It represents more than 99% of the total matter in the universe.
Okay, so this video was for a commercial group trying to get funding basically for their reactor, but it was cool. I mean, it shows the kind of little donut part, and what happens is the plasma kind of races itself around the donut. You can see in the picture in the left, there's a little worker there. The plasma would be inside there when the reactor was on, and on the right-hand side, you see the outside, and again, just a massive collection of electrical fields and magnetic fields and stuff like that to make it happen. In November of 2015, at the Max Planck Institute in Germany, all right, they actually were able to create more energy out than they put in. And it wasn't a lot, but this is very promising because this shows then that, hey, maybe plasma is going to be a viable source of energy one day. So again, I'm hoping that this is going to happen sooner more than later.
In the nuclear fission of uranium-235, a neutron collides with a uranium atom, causing it to fission into two smaller nuclei. On the average, 3 neutrons are emitted for every U-235 atom that divides.
I think of fusion as the energy source of the future, because if they could get it to work, it would be very clean. You wouldn't have any problems with it. But there is an alternative energy source, which is fission. And when people talk about nuclear power, it's almost always about nuclear fission. And in a fission reaction, you're going to have a heavier element, which is basically essentially trying to get closer to that iron 56. And so in this example with the picture down there, it's a uranium-235. They always need some kind of a trigger, which is usually a neutron trigger. You can think about the neutron as just smashing into the heavy element. So the heavy element will break up into smaller pieces. In this case, it goes into a barium, a krypton, and you have 3 neutrons. So notice here that you needed a neutron to start the reaction, start the party, all right? And that neutron created multiple neutrons afterwards. So when you're doing doing fission, first of all, you have to realize you're going to create more neutrons and you have to have some way to contain them. And also, you're going to create other types of elements. So fission does create energy. People have been successful at harnessing nuclear fission to get energy out.
5, 4, 3, 2, 1, fire.
The blue light you saw in the video is from, I think it's pronounced Cherenkov radiation, and that's a type of a radiation that happens when you have a nuclear fission reaction. I am amazed that someone took this video. Apparently they were right there because you could hear him talking. That would kind of freak me out because these kind of processes are very high energy, and the water would absorb a lot of the particles, but I worry about them being exposed to other kinds of particles. But anyway, you do have these kind of cool effects, which is pretty cool stuff.
If the mass of U-235 is less than the critical mass, no chain reaction will result. Most of the neutrons will escape to the surroundings. If the mass is critical, most of the neutrons will be captured by other U-235 atoms, and an uncontrollable chain reaction will occur. This is the explosion of a thermonuclear bomb.
In a fission reaction, you have to control those excess neutrons. If you don't, the neutrons react with other uraniums, and more neutrons are created, and they react with more uraniums, and it goes on and on and on until you get to what's called a supercritical chain reaction. And that's a radiation process that just can't be stopped, basically. So in a controlled reaction, they'll put something in there to kind of hold on to the neutrons, all right? Some kind of a neutron sink, if you will. The other problem, though, with fission is that you do end up with these other heavier elements left over from the reaction. And the waste products are super radioactive unto themselves. And you have to get rid of them. You have to store them usually in some kind of a hillside or something. There's some other scary things that people think about happening. However, it is a viable source of energy. And there's more than 400 nuclear fission plants in 30 different countries. In the United States, as we'll see, there's both pro and anti-nuclear fission people out there. There's been some issues with nuclear fission plants in the past in the United States. However, that was quite a few years ago. And just like computers have gotten better in the last couple of years, well, since the problems occurred in the United States, the computers have gotten better and all the technology as well. So proponents think that we should try it again and then create energy and stuff like that, which would be cool. On the other hand, there's a lot of people that remember the problems, and there's both yeas and nays. And again, like a lot of things, I don't care which side of that argument you wish to stand on. Just realize, try and use science to make your decisions and not just raw emotions.
Located in the nuclear core of a fission reactor are fuel rods, moderator and coolant fluid, and control rods. Each fuel rod contains tiny pellets of uranium dioxide. In these hundreds of fuel rods, fission occurs, producing an average of 2.5 neutrons per fission reaction. The fuel rods are surrounded by water, which acts as a moderator by colliding with the neutrons and slowing them to a low thermal level. The water absorbs the thermal energy, which is used to drive a steam turbine to generate electricity. The low-energy neutrons enter other fuel rods and collide with uranium-235 nuclei, creating additional fission chain reactions and the release of more neutrons. The amount of low-energy neutrons present is regulated by control rods made of boron, which are very effective at absorbing neutrons. These rods are raised out of or lowered into the core as needed to sustain the chain reaction at the desired level.
So in this example, they used boron rods to absorb the neutrons, all right? And boron is apparently pretty good about absorbing the neutrons, so you don't have the excess out-of-control reactions. You still have the waste results and stuff like that. So in my vision of the future, I hope that fusion is going to be the energy of the future because it's cleaner, but we have to master that plasma stuff. So in the meantime, fission is a possible commercial alternative, but I need to talk about some of the problem events that have happened in nuclear fission. The first one was actually in 1979 in Pennsylvania. It's the 3 Mile Island incident, and one of the reactors there really started to go kind of crazy. And again, I'm not going to talk about any of these in great detail, but if you're interested, 3 Mile Island is definitely something that happened in the United States. Then in 1986, there was the Chernobyl incident in Ukraine, and that was pretty bad. And HBO did a really cool series about this and stuff that was part fiction, but based on a lot of fact, really freaky for me as a scientist to watch that. Then in 2011, there was the Fukushima plant in Japan, and that was a result of a tsunami that came in, made the reactor go bad, and a whole area had to be evacuated, stuff like that. But even more local to us here in Oregon, Hanford, Washington, which is in the southeast corner of Washington roughly, is a place where they created a lot of nuclear material for some of the nuclear bombs as well as some medicine sources. And that is a huge source of environmental contamination. And if any of that stuff, which is being stored up there in tanks, were to leak into the Columbia, it would then go down to Portland, all right, where we have fish and some places have drinking water and all kinds of stuff. So all of these are things that have to be considered. And these are all fission problems because the results, the leftovers, the parts you don't want, are very difficult to get rid of. Lita Mitner is an unsung hero of nuclear chemistry that I want to talk to you about real fast. Lita Mitner was a woman in a very male-dominated field at the time, but she was one of the people that helped to explain what fission is all about, and it was 1938. She worked with Otto Hahn, Fritz Strassmann, and Otto Frisch at the time, and they were the ones that created the understanding exactly of what fission is all about. Element number 109 with the symbol MT is named after Mitnerium, and that's kind of cool. So she's a powerhouse in this field. And again, at the time, it was very male-dominated, so with her to do that was pretty fantastic. Like Marie Curie, who we talked about in Chem 221, she was forced to work in a basement because she was a woman, all right? She never got the Nobel Prize for the process of fission. Otto Hahn did, so she was basically looked over. And that's really sad, man, because she apparently was just as active and involved in all this stuff as everybody else did. Lita Mitner was neutral in World War II. She didn't wish to take sides. And so some people think that she was looked over because she didn't take a stand, Allies versus Axis. I don't know about that. But anyway, I do think she deserves more credit for her work. Nuclear fission is where all the nuclear power plants and stuff basically have come from, her understanding and developing of the fission idea. So alas, kind of cool to give her a heads up and a thumbs up for the work she's done.
Even some everyday objects contain radioactive sources. Let's see how a Geiger counter responds to these items. First, we look at the background reading. Listen for the rate of the counter clicks and observe the meter response. Smoke detectors use a shielded americium-241 source. Smoke detectors should never be disassembled, as has been shown here for demonstration purposes. Now we observe the response of the Geiger counter to a lantern mantle. Lantern mantles can be obtained at any sporting goods store. This brightly colored orange Fiestaware plate contains uranium oxide in the glaze. The radiation level is high enough to be dangerous if exposure is prolonged. The blue Fiestaware plate has a non-radioactive glaze.
This is a kind of fun video that shows, first of all, a Geiger counter. And a Geiger counter is something we showed in an earlier video, but it's a way to detect radiation. And in the picture on the right there, you can see that in the Geiger counter, you have essentially like a type of gas, argon gas. And as radiation comes through, it basically makes ions. And the ions can be detected. You have a cathode and an anode. And so the ion has a positive, negative charge. So that creates then like a current. And that makes kind of a beep, the click, click, click kind of sounds in some of them or something like that. Anyway, a lot of substances have radiation around us right now. Orange Fiestaware is a good example of something you can find at a lot of stores, even in Gresham, that I would be very careful with. And one time I was in Walport, Oregon with my family, and we were in like a secondhand store just kind of looking around. And all of a sudden, here was a bunch of orange Fiestaware. And oh, it looks kind of festive. I instantly grabbed my son, who was young at the time, and I pulled my wife and I said, "We're out of here, man," because orange Fiesta ware usually has a uranium coat of paint on it, and the uranium has a little bit of radiation on it, and you certainly wouldn't want to be eating from it. If you are using orange Fiesta ware right now and it's older, I would recommend getting rid of it and getting some new plates, because you don't want these radioactive sources on your food all the time, because you'll eat them and radiation goes inside. All right, paranoid chemist, whatever. Health is a big part of radiation studies because all of these things are very high energy. And there's multiple ways to talk about radiation when it comes to health. Here's just some of the examples, and there's more. The Roentgen, which gets the symbol capital R. Curie, which is capital CI, named after Marie Curie. There's rad and rem and others and stuff like that. So the Roentgen, which is named after the developer of the X-rays, is a measure of how radiation exposure is proportional to air ionization. So as an example of this, a chest x-ray is about 0.1 R, all right? And people can calibrate number of Roentgens and stuff like that. REM is the Roentgen equivalent for man or people, humans, all right? Anyway, REM is related to Roentgen. The Curie is the one that I've had the most experience with. 1 Curie is the quantity of any isotope that undergoes 3.7 times 10 to the 10th DPS. DPS stands for disintegrations per second. Sometimes it's also decompositions per second. But because one atom is disintegrating or decomposing, you would have 3.7 times 10 to the 10th atoms decomposing or disintegrating per second. A rad is equal to so many joules absorbed per gram of material. So a rad is just 1.00 times 10 to the minus 5 joules. And if a person gets 450 rads, this creates what's called an LD50 for humans. LD50 is something that's used in medical fields. It stands for lethal dose 50% of the time. So if we had a whole classroom of students and we all got 450 rads, half of us would be dead. That's what a LD50 means. It's kind of scary. So too much radiation, of course, can be bad. Try and stay away from the LD50 value. So here's a type of a question that I want you to think about as well as answer. And the question says we should try to live as radiation-free as possible. All right, let's just go through these. A, yes, all radiation is bad and it's best to have no radiation at all. That's ridiculous. The Earth creates radiation. The elements deep in the Earth also undergo nuclear reactions. Radiation comes up from the ground at us. In addition, things in the sun and different kind of astronomical events will create radiation that comes down from the top to us. So staying away from radiation is just ridiculous. All right, don't even think about that. We live with radiation all the time. So B, yes, we should try and be as radiation free as possible, but we do gather some radiation exposure naturally due to geological processes and from space, so some radiation exposure is natural and normal. I would argue that answer B is definitely the best case. You do want to try and stay radiation free, all right? You don't want to go next to a nuclear power plant without protection and stuff like that. On the other hand, do realize that even taking an airplane flight from Portland to Boston or something, that's going to make you exposed to some radiation as well. As you get higher up, you've got more exposure and stuff like that from things. The other ones are just kind of silly. C, no, we can trust the government to tell us what is good amount. I don't think I'd always trust the government here. Sometimes governments are, of course, subject to political pressures, so I don't think that would be a fair statement. I hope that the government would help us out, but you never know. And then D, no, I want to be like Peter Parker. He was bit by a radioactive spider. Well, yeah, heck yeah. But no, of course, that's not real. And then E, no, I want to be like Bruce Banner. Bruce Banner, who was the Hulk, was exposed to gamma rays. So those are just all silly answers. But I put this question up here because I want you to realize that you will be exposed to radiation. You're probably being exposed to radiation right now, all right? So you want to try to keep radiation out of your world as much as possible, but some of it's natural, all right? Our bodies are used to some radiation. That's one thing. We grew up in the earth. Our species has grown up, evolved, and stuff like that. Some radiation is going to be natural and normal. We don't want to be exposed to excess amounts, but a little bit, okay. So don't be deathly afraid of radiation. Just do your best and stuff to try and get away. Unfortunately, there's no guarantee of superhero abilities. Darn it. So, alas. Transforming nuclear elements is a big part of science, all right? It's some chemistry, it's also some physics. You can use things like a linear accelerator or a cyclotron to basically create heavier atoms from lighter ones. And these are really cool areas of research. On the lower right-hand side is the cyclotron, and the cyclotron basically spins an atom in faster and faster and faster areas until it gets to the target. And as the atom smashes into the target, then some small percentage of the combined target with sample things will make heavier elements, which is a really cool thing. This is a really neat area of research, and if this is anything you're interested, I would definitely encourage it for like a graduate study. The most famous of the accelerators is probably CERN right now. CERN is over in Switzerland, all right? And again, it's a massive, massive circle. But again, that circle that you're seeing in the picture right there, that circle is just where you're accelerating some kind of a sample, and it's going to smash into some kind of a target. And they can use this to detect if there's other kinds of subatomic particles, so like the elementary particles, quarks and stuff like that. But they can also make other elements too. It just depends on the type of experiment they're looking at. Astronomers and chemists talk about how elements are made. This is an area where the two come over. And this is a really interesting area of research too. Now, up to iron, you've got the thermodynamic thing, the limit going on. And so that's when the normal star processes, so like our sun around our Earth will go up to iron before it stops. But there has to be a way to rationalize why we have so many other elements out there. So for example, gold and silver are both elements past iron. How the heck do we have so much? And molybdenum, which is actually a main ingredient, a big important ingredient in our body, is also important, plus the uranium and plutonium and stuff like that. So they have different kind of theories about how these elements were made, and this is definitely an area of research as well. I like this term, a kilonova, which I hadn't heard until relatively recently. A kilonova is when two neutron stars supposedly collide into each other, and they feel that kilonovas might be responsible for many of the post-iron elements on the Earth. I don't know, pretty exciting. But if nothing else, it is important to remember that our bodies are made of the stuff of stars, because all of these elements had to come through fusion reactions and stuff like that, or sometimes fission. Most of these things happened in space. So your body right now is the product of solar things. We're made of star stuff. Kind of cool.
My main MC, Alpine Cat.
With the serendipitous B.O.B.
Mr. B, drop the beats.
As teaching is one of this lab's main themes, it's the place to introduce me to physics with beams. They accelerate nuclei, the protons and neutrons at the centers of atoms. We call them nucleons. Protons define the element, it's chemistry. Neutron numbers affect elements with subtlety. They define the isotopes, and with effort they hope to make some that no one's ever seen before, and that's dope. So you know the elements from the periodic table, but this other version highlights isotopes that are stable. The isotopes we know are on a diagonal track, and at first glance, I thought it looked pretty whack. But as you get away from that stable nucleus line, there's radioactive isotopes we don't usually find on Earth, because these nuclei prefer to decay into more stable isotopes by tossing particles away before they can. The teams here check out their dynamics, measure masses and lifetimes, and study their mechanics. They're building F-Grid with mysteries to solve, like what reactions drive stars, and how do they evolve. The strong force finds nuclei, but we still can't say exactly why some are stable while others decay. A more powerful machine can push the frontier. The physicists here, they get nuclear. So let's say you were making a new kind of nucleus in EFRID, a plant facility that's long been discussed. The starting atoms, they're just ordinary, stable isotopes. They're easier to store and carry. You strip off their electrons for a charged state. They zip through electric fields made to accelerate. Then you slam them into something. We call it the target. 5% of your nuclei are gonna really hit it. Those that do will be different from your starting crew. They've lost protons and neutrons, or maybe gained a few. All kinds of fragments have just been created, so you put them through a magnet that can get them separated. If it's got lots of protons, it takes an inside curve, but more neutrons tend to drag it for an outside swerve. You filter out the isotopes you don't want in the stream, and voila, you got a rare isotope beam. And to put your nucleus on the nuclear map, you'll then measure it in a detector or trap. This facility is for research and to teach, so that you could be more than just a figure of speech.
Okay, this video is very fun, and it actually goes on longer, but I don't want to keep your attention that long. If you're curious to see the full video, you can see the YouTube link right there. This video comes from Michigan State University, where there's the National Superconducting Cyclotron Laboratory, and this kind of talks about a lot of the things we've looked at in this section so far. They're basically taking samples and accelerating them to just incredible energies, smashing it into the target, and 5% of them are really gonna hit it, which is what she said. I love this. Anyway, the 5% are what they're after. So they try and detect them to try and find heavier elements and stuff that haven't been seen. And you could see there, they showed briefly the peninsula of stability and the sea of instability around it. They are after, arguably, looking for those islands of stability that may be out there too. And who knows, maybe they'll find it. It's pretty cool stuff. This is a great place to do research. It always looks like there's a lot of fun going on there. If this is your thing, I encourage you to check out Michigan State University.
After graduating from UCLA with a major in chemistry in 1934, I went to Berkeley to obtain my PhD in chemistry in 1937. And then a few years later, I became involved in the research to synthesize and identify the so-called trans-uranium elements. Uranium has the atomic number 92 and is the heaviest naturally occurring element. And what we did was go on to produce by nuclear bombardment elements with atomic numbers greater than 92. For example, 93, 94, 95, 96, and so forth. The most important one, of course, is the element with the atomic number 94, plutonium, which has the fissionable isotope that is used in atomic energy and was used in the atomic bomb that brought an end to World War II when it was used at Nagasaki. We named plutonium after the planet Pluto, just like uranium had been named after Uranus and neptunium after Neptune. We could have given it the name plutium after the root Pluto, but we like plutonium better. And we should have given it the symbol PL, but we like PU better. And we thought maybe we would be criticized for giving it that kind of a symbol. We went on, after I moved to Chicago to work on the chemical processes for the separation of plutonium for its use in the atomic bomb, to the metallurgical laboratory of the University of Chicago, and here we went on to discover the next two elements with the atomic numbers 95 and 96. And in order to do this, we had to predict the chemical properties using the periodic table, but the form of the periodic table at that time was wrong, and I changed it and created the actinide concept for placing the heaviest elements in the periodic table. For this, I received the Nobel Prize in 1951, so that shows you how easy it is to do work that would give you a Nobel Prize. One of the elements that interests me very much that was synthesized is the element with the atomic number 106. which has been given the name by the discoverers, of which I am one, Seaborgium, with the symbol SG. The Commission on Nomenclature of Inorganic Chemistry of the International Union of Pure and Applied Chemistry that have to approve this name rejected it because I'm still alive and they could prove it. But there was such a universal disapproval of that action that it now looks like the name Seaborgium for element 106 is going to remain. And of course, I'm very pleased about that. This is a very high honor. I think it's a greater honor than even receiving the Nobel Prize, because it'll last forever. The name Seaborgium will be in the periodic table 100 years from now, 200 years, 1,000 years from now. Actually, a total of 20 trans-uranium elements have been synthesized since that first synthesis of element 93 and 94 in 1940 and 41. So that now we're up to element 112. And it looks like it's going to be possible as the years go on to synthesize and identify perhaps another half dozen transuranium elements. I think this will occur after I'm gone, but perhaps during the lifetimes of many of you, and perhaps some of you will be involved in the discovery of these additional transuranium elements.
Glenn Seaborg is one of my heroes of science. In the chemistry world, he's probably as famous as like Einstein is to the regular world. Seaborg's work is a little bit more esoteric maybe, but anyway, he was really, really cool. And he went to a community college, all right, in California before he went up to Berkeley, where he just exploded scientifically and helped to synthesize and discover a whole bunch of the heavier elements, the post-uranium elements he talked about. Pretty cool. At the time, the periodic table did not have an actinide line, and he basically rewrote the periodic table, which was no small feat, but he did get the Nobel Prize, which is pretty awesome. Then, towards the end of his life, they nominated him to be the element, to be named with the element number 106, Seaborgium. And at the time, the groups that were in charge of this said, oh no, this can't happen because Seaborg is alive. And when elements have been named after people in the past, it was always because people were already passed away. Well, the outcry was just fantastic because Seaborg was really popular and a powerful force in chemistry. So they eventually then they did remit and they did name element 106 after him, and he found out right before he died, so it was kind of cool. But anyway, Seaborg was really cool. And remember, he did go to a community college, all right? And he went on to become one of the most powerful, famous, and just awesome people in chemistry of all time. He has some autobiography works if you're curious to read more about him. Pretty cool individual.
Suppose you've discovered an ancient bone amulet in an archaeological dig and you want to know its age. You can use the rate of decay of carbon-14 to determine the artifact's age. The nucleus of a carbon-14 atom is unstable. At some time, this unstable nucleus will emit a high-energy electron called a beta particle, which has a 1- charge. The beta particle causes a neutron to change to a proton, and the carbon-14 atom then decays into a nitrogen-14 atom. The average time for half of a group of carbon-14 atoms to decay is 5,730 years and is called a half-life. Your bone amulet is found to contain only 12.4% of carbon-14. How old is the artifact? The level of 12.4% indicates that 3 half-lives have passed. 3 half-lives times 5,730 years is 17,190 years old. Carbon-14 samples can be accurately dated up to 60,000 years old.
Most of carbon is carbon-12, but there is carbon-14. And as a living being goes around their things, carbon-14 is you exhale it, you get more in, stuff like that. So it's constantly going back and forth. However, once the sample is dead or whatever, then there's no more exchange of carbon-14. So you have like a steady state of carbon-14 basically decomposing. And the half-life of carbon-14 is very well known at 5,730 years. So in 5,730 years, you'll be down to half the carbon-14. Another 5,730 years, you'll be down to 25%, et cetera, et cetera. So they can date things with carbon up to about 60,000 years old. That's the level of technology. Some of the more recent things have been contaminated because we have so much carbon emissions from fossil fuels that in the last 100-ish years, the carbon dating doesn't work as well. But for things, outside of the 100 years up to 60,000 years, carbon dating does a really great job. Carbon dating is what they used with the Shroud of Turin originally to try and tell it wasn't as old as they thought it was and stuff. The thing about radiocarbon dating, though, is that this is a carbon system, but you don't have to be limited to just carbon. So if your object has other kinds of elements inside it that are radioactive, there's other kinds of systems you can use to see how old something is. So you're not limited to just carbon. You can also look at other isotopes, how they decompose. It's a pretty cool field.
In positron emission tomography, radioactive tracers emit positively charged electrons called positrons. These positrons encounter electrons and they annihilate each other to produce two gamma particles. Gamma particle detection from several angles in conjunction with computer imaging produces accurate images of soft body tissues. PET is particularly useful in diagnosing Alzheimer's disease in brain tissue. Nuclear magnetic resonance imaging, or MRI, is a popular diagnostic technique because it does not submit the body to dangerous high-energy particles. MRI is performed by placing the person in a large cylinder that contains a strong magnet. The magnetic fields of the atoms of the body are caused to resonate by the introduction of radio waves. A computer interprets the signals put out by the resonating atoms to produce a two-dimensional view of the body. The MRI is especially useful in detecting abnormalities in soft body tissues.
Medicine benefits from nuclear science, just like most fields do. In medicine, two of the main ones, there's probably other ones too, two main techniques are PET and MRI. And PET stands for positron emission tomography. It involves the creation of a technetium, which is metastable. And as we talked about earlier, things with a little m right there, they will decompose to regular technetium and a gamma ray. And the gamma ray, as it's emitted, then a detector can detect the gamma rays coming out, and you can get some kind of imaging of soft tissues and stuff like that, which is cool. The half-life for technetium-99m is 6 hours, so it goes out of the body pretty fast and no problem. MRI, magnetic resonance imaging, and its related counterpart, which is called NMR, nuclear magnetic resonance, these involve types of transitions in the nucleus, but there's no radiation evolved, all right? You're actually having some of the spins flip, the nuclear spins, to create some really cool kind of effects. So MRI and NMR and stuff, they're not traditional radiation things, but it does involve the nucleus, so that's why it's placed inside there. Some of you have probably had an MRI done before. It's pretty common. It can have some really cool information on what's inside your body. So yeah, lots of uses of this kind of stuff, which is pretty exciting. Okay, that's the end of chapter 21. I really appreciate you spending your time with me, and hopefully it's learned a few things along the way and stuff, which is cool. I do encourage you to check out the study guide, which is a bulleted list of highlight guides, just to make sure you got this all down, as well as the concept guide, where there's some worked problems. You can see how the questions can be determined. Following these notes, there are important equations from the different sections, and also there's some end of chapter problems. So questions, the answers are on the next page. Try and do the questions yourself, see if you get the answer, stuff like that. If you need help in any of these topics and stuff in this section, definitely reach out. You can email me at any time or talk to me during office hours. You can also talk to the Learning Success Center /Avid Center at Mount Hood. They have people there to assist you as well. All right. Good luck with your studying. Have a wonderful day.